All right, hello and welcome. College Physics 1, Physics 1401. Let's start this course with some basic mathematical background. There are many things to consider. Let's start with really basic stuff, like how do we represent numbers and variables. Basically, how do we represent physical quantities in terms of numbers, and how do we represent numbers in terms of variables, okay? After all, physics is all math. Okay, so let's start with really some basic things. Like, let's say you go out for a walk, okay? And you walk with a steady pace, all right? And then you keep time, okay? You want to know how much you walked, all right? Let's say you walk for 20 minutes, a 20-minute walk, and you end up walking 1 mile, all right? So you know that if you keep like that, if you walk for more, like 40 minutes, let's say, it'll be 2 miles, okay? An hour, 60 minutes, you'll finish 3 miles, you know, right? Easy, relaxed walking. Okay, so these are numbers, 1, 2, 3, 20, 40, 60. Without the unit that is attached to it, which are these are the units. Well, we can't do much with these numbers, okay? You gotta know what they represent. So in this case, we have 2 units already, miles and minutes. Okay, these measure time. These measure what? Distance in this case. We could measure time in seconds if you're playing basketball, right? A minute is really long. Or you could measure the distance in feet, right? Inches, or better in meters, or kilometers. Okay, you have many options. Now, well, what do we know from this data here? This is our data that we collected from our exercise, all right? Now we see a trend, right? I mean, 20 minutes in 1 mile, walk for 40 minutes, 2 mile. You're making the numbers bigger, okay? What can change here? You can't change time, right? Time is running, time keeps running. But the distance you walk within a given time, depends on how fast you walk, right? So it depends on how fast you walk, but it depends on time as well, right? So time is independently running by itself, but the distance covered by you depends on the time elapsed. It's a dependent variable. Okay, that's a quick observation. Another observation is, okay, I see a regularity here, right? Going from 20 to 40 to 60, the miles go like 1, 2, 3. If I triple the time I spend walking, I need to multiply the distance traveled by a factor of 3, okay? So factor is basically the number you multiply your numbers with. Right, a very rough definition of what a factor is. You're scaling, okay? Let's write here, scaling the number. I mean, this could be the length of a pencil, right? Let's say this is, 7 inches long, you know? I can't stretch or compress a thing, but imagine I could, all right? A rubber band, I could stretch it, so I could double the size, right? Scaling means multiplication by a factor of 2. So means multiplication. Now you can scale up, multiplication, or you can scale down. You can squeeze an object. All right. So the variable changes. Now let's use letters instead of numbers. That's the thing about math. Okay. Whenever you start using letters instead of numbers, things start getting complicated. And in order to do physics, you have to do that, and many other sciences, and math itself, okay? It's never just numbers. This is not about punching numbers in a calculator. It's about the concepts, the relationship between physical quantities, measurable quantities, they're all measurable quantities, and formulas and all that. All right, so we need a letter. Now, what kind of letters? We have the English letters, the alphabet, A, B, C, and all. And once you're done with these, you can start using the Greek alphabet, like alpha, beta, gamma, delta, so on and so forth, all the way to omega, right? And these are the small. You also have the capital versions, like a capital omega would be like this, delta, like that, gamma, so on and so forth, all right? And of course, there's X, Y, Z on the other side of the English alphabet, all right? They are used a lot. So let's use those for this part of the data. We have distances. Okay, let's use the letter X. Okay, let's use this guy here, X. And for time, let's go with T, right? Let's use the variable T. Now, when we start using variables, we gotta be careful, okay? Because you have two options, basically. Option one, X can be any number. Any number. Okay, it can represent all these numbers as long as you keep walking. The distance covered from the starting point could be your X. So X represents that. In that case, T would represent what your stopwatch says. You can start walking and start your time, and then after 1 hour, T says 60. Fine. So T can mean any number as long as you know your starting point. Okay. So you may have a distance in the spatial dimension. Okay. Spatial variable, distance. A spatial variable could also be the position, all right? I'm going to talk about that difference in a little bit, but location, position, length, distance, these are all in the same category of X, what is represented by X, okay? And same thing for T. Now, we don't have much flexibility in T, really. T just does its own thing. I mean, time keeps running, all right? You can't help it. Even if you're not walking, time keeps running. But still, at least it's increasing, we know that. So it has a direction, in a way. It gets bigger, all right? So that's option one. Option two, and both are valid, actually, used a lot. X may mean one of these numbers, okay? X refers to one specific point, okay? Value. But then, what about 2? If X is 1, let's say in our data table, if X is 1 mile, or MI for short. Okay, like we use MIN for minutes, we can use MI for miles. What about 2 miles? That's not X anymore because we used X for 1. Okay, now we gotta change the letter. Okay, but I don't want to pick a different letter, Y or A or B or Greek, that it's gonna get all over the place, all right? I don't want to be like that. I want to still use X, but I'm gonna add, okay, I can add an index, okay? Now let me draw bigger here, X. I can put a letter here, a letter or number, or I can put something over here, okay? Like I could put a 0 here, or I could put number 1, 2. This is actually very convenient because I can go all the way up to any number, X 135. Okay? This means I have a separate X for each number here. This is X1, X2, X3, so on and so forth. Okay? That's one way. Another way is using a symbol up there. Like I could put an apostrophe or a prime. I call it X prime. Okay? This is called X prime. Or I can put 2 of those. Now these are depending on the convention. People, the book likes some way, okay, and you may like something else. So you may call this one X double prime. I'm sure you're familiar with these in math, but let's just review, right? X double prime. X double, that's how you name it, prime. Or X triple prime, why not? Well, after 3, you don't want to put 4, it gets cluttered, so you may switch to something else. How about this one? You put something above, okay? You can put a bar on top of it, call it X bar. Or you can put a wavy bar on top of it, the symbol tilde, call it X tilde. Okay, there are many ways to do that. Let's use prime, okay? So X is 1 and X prime is 2. So let's leave option 1 for a moment, but let's focus on option 2. So every letter I use here, every symbol, okay, corresponds to a different data point. And then let's use double prime 2. X double prime is 3. Now going from one to another is what I was trying to explain earlier, the scaling, okay? So instead of saying X prime is equal to 2X, or instead of saying X double prime is equal to, 3X, okay, I can keep going like this. If I want to write X double prime in terms of X prime, I could do it again, right? Going from 2 miles to 3 miles, I need to multiply 2 by 3 halves, right? So 3 halves multiplied by X prime, which is 2X, gives me 3X, which is what I just wrote there. Now, when I multiply these variables with numbers, I'm avoiding the cross, okay? Because obviously I have an X here. I don't want to confuse myself and you, so I'm not using this for multiplication. I'm not going to do that, okay? I'm just going to use parentheses. So the general rule is if you're only using the letters like A and B, if you just write AB, you mean A times B, all right? Unless A has a special meaning, okay? And we're going to talk about this guy here, delta, in physics And math, delta has a meaning. So if I write delta B, it is not usually delta times B, but it's just one variable. I'm going to explain what I'm talking about, right? So when you have letters, you just write them, and it means multiplication. And if you have numbers, especially with fractions and all that, it depends. I mean, if you can get away with avoiding brackets or parentheses, yeah, go for it. Let's say 2/3 A. All right. Well, 2/3 A is the same as 2A over 3. Now you can't see it because my video is on the way. All right. So let me move it to the left a little bit. Okay. So I was saying delta B doesn't mean delta times B, but it means something else. And for multiplication, A times B can be just written like this. If you have fractions, you can do it like this. Or 0.25 times 42.6. You can use parentheses like that. Anyways, let's go back to this here. So we have our x values. So to go from one x to another x, we're just multiplying by a number. This is what we call a factor, okay? This is called a factor, or a scalar, because it scales it. It changes the magnitude of that quantity, let's say. It changes the value. Well, same thing can be applied to t as well, because our time values, remember, going from 20 to 40, going from 20 to 60, it's scaled. Now, whenever you're doing this scaling, these numbers don't come with units, right? I mean, x has a unit, it has distance, but the number 2 here does not have a unit. We call it a dimensionless number, or dimensionless quantity. Dimensionless, okay? Dimensionless. So the word dimension here is related to the unit that I was telling you earlier, okay? Feet, inches, meters, kilometer. These are all describing a spatial quantity. They all have the same dimension. They may have different units, but the same dimension. It's pretty much length. Okay, so we're going to call it L. L. And in order to denote that it's not just some arbitrary variable, but it is a dimension, I'm going to put square brackets around it. Means the dimension, length. So for time, I'm going to do the same thing. It could be seconds, days, minutes. Unit may differ, but they're all time. So square brackets and t. Okay? And you can define other dimensions, which we don't need right now. But mass, for instance, that could be m, capital M, in square brackets. Okay, the video is breaking up every once in a while. Sorry about that. Okay, so yeah, so these are the dimensionless quantities, these numbers. A scalar is a dimensionless quantity. So whenever you multiply a dimensionless quantity, a scalar, by a quantity that has a dimension, you also get a quantity, or let's say another number, that represents the same kind of quantity with the same dimension. Okay, so if you have meters on this side, you'll get meters. If you have feet, you will get feet there. Same thing applies to time. Okay, going from 20 minutes to 40 minutes, you're scaling it by 2, so you can write it as t prime is equal to 2t. A dimensionless quantity, or equivalently, you can say its dimension is equal to 1. I mean, does it have dimension or not? Well, if it has a dimension that is represented by a letter, we have those. It's either L or T. But if it is not like that, we say it's equal to 1. All right? And the reason for bringing this 1 up is because when we do math with these variables, the dimensions that correspond to those variables also follow the same rule. Okay? As long as you're not violating some basic principles about dimensions. It's about comparisons, okay, like apples and oranges. You can't add or subtract them, okay? If you have two physical quantity that have different dimensions, you cannot add or subtract them. This is meaningless. T plus x. You will never see something like this in physics. Never ever. Or x prime minus t prime. It's wrong. You can only add or subtract physical quantities of the same dimension. Now this may or may not be useful here, but it is totally fine, okay? Because both are in minutes, let's say. Now this rule doesn't apply to multiplication. You can multiply them any way you like, okay? You can multiply time and distance, or you can better, let's see, use something that you're familiar with. You can divide distance by time and you will get speed, okay? You may say I'm making 3 miles per hour because that's what you have here, right? So division and multiplication, okay, but when you're adding or subtracting, the dimensions should agree. So when you're multiplying t, which has the dimensions of seconds or time, let's say, with a dimensionless number, so the dimension here is 1. That's what it means, right? Equal to 1. 1 times t is t. So in order to treat these scalars in a way that you can apply algebraic rules, you say its dimension is equal to 1 because it's dimensionless. All right. So this scaling involves this factor, which we call scalar. Now, can we use a letter to represent this as well? Since we're using letters for everything, right? Yeah, sure, why not? Okay, I mean, why don't we use, I don't know, let's go back to that list here. Why don't we start using those Greek letters now? Alpha, beta, gamma. Let's use alpha. All right, alpha. We have x here. Let's say x prime is equal to alpha x. Okay. And for t, let's do the same thing. T prime is equal to beta t. Now you may say, hang on, if in my table I have these numbers here, 1, 2, 3, and 20, 40, 60. So to go from 1 to 2, I multiply by 2. To go from 20 to 40, I also multiply by 2. So alpha and beta are the same in this case. Yes, they are, you're right. Alpha and beta are the same, which is equal to 2. Okay? Now, is it always the case? Well, it depends on your data. I mean, I'm just considering the data I got from my little walking here in the park. Okay? So, what are the ways of representing this data? let's think about that for a second. Representation of the data besides the table, all right? Well, I could use this. I could use these lines and place my time values here on this axis, and then the distance over here. And then the x values here, let this be, I'm sorry, the time values here in minutes, 20 minutes, 40 minutes, 60 minutes, and then 1, 2, 3, these are the miles, 1 mile, 2 miles, and 3 miles, right? So this point here represents the pair, the row in your table, right? In your table here, this row corresponds to that point. The second row, 40 versus 2, is another point. 40 minutes and 2 miles, and then 60 minutes and 3 miles. Okay, they all line up actually, right? Now this representation is called the graphical representation, has some advantages. Okay, if you're just given a bunch of numbers in a table, you just look at the table and you may not see some relationships that fast, but if you see all these dots lining up, okay, you really want to connect them, right? Now when I say connect, I'm not talking about just connecting the dots, because like this one here, for instance, if I have a dot here, a dot there, dot there, dot there, okay, I don't want to do this, okay? I mean, you will rarely see this in physics. What you really want to do is, if you have a point distribution like this, you want to go in between those points, okay? You're going to average them in a way that some of are in this direction on the left, some are on the right, okay? So you're honoring all of your data points, but you're still fitting a straight line. A straight line or a linear fit, let's say. There are other fancy names for this, but let's leave it for later. Linear fit. So in this case though, because I chose my numbers, you know, this way, the linear fit does actually go over the points themselves, right? So I can just go like this. This is my straight line. But the advantage is now I know what's going to happen here. If I go for a walk and it's like an hour and 20 minutes more, which makes 80 minutes, then I go up and find that point on the left, this axis, which will be 4, right? I'm just counting boxes here. I can predict that I will walk 4 miles, or what happens in between, okay? Let's say at 30 minutes, half an hour, I will be at 1.5 miles from where I started. Okay, so that's the graphical representation, and there are other things you can do with this graph. But before that, let's go back to these two equations that I just wrote here, t prime for t prime and x prime. Now, that is two numbers are multiplied, giving me another number. Can I write this equation, or can I write the x prime, not in the form of a multiplication, but addition, all right? I still want to represent a change from x to x prime, which is alpha x, but I want to write it in a different form. Okay. Now x changed. Okay, let's say from 1 to 2 to 2 miles. What's the difference? Okay. So you can go subtract 1 from 2 and get 1 mile, or you can subtract 1 from 2 and get -1. Okay, they will tell you the difference. One has a negative sign, but you don't want ambiguity in these definitions. Okay, so the convention is when you're talking about differences, you want to subtract the old from the new, or after minus before. Okay, so in our case, x prime minus x. Okay, so this is a later time, this is before. So after minus before, and call this the change. So we don't use this one, but we use that one. Okay. Well, this is not to mean that our changes will always be positive. No, it can be negative. But I'm just picking the later one and writing it first. All right? So let's say after minus before. This is the convention here. Now this is the change in x. Okay? And the change in x is too long to write. I want to abbreviate it to another letter, but I don't want to use a letter like YZ. Okay? I still want to keep the letter x in it. So I'm combining two letters. I'm combining the Greek letter delta and the letter x together and calling it delta x. Okay, so delta x means the x later, x prime minus x. Okay, delta x is not delta times x. Delta x is just one variable. That is the difference. All right. Now, I can do it for any quantity. Okay, it doesn't have to be distance. It doesn't have to be distance. It could be applied to any variable. If I'm going from t to t prime by scaling, okay, this one is also equal to alpha. Remember, alpha and beta are the same. So this means t prime minus t is now written as delta t. Now I add t to both sides. So what do I get? T prime is equal to t plus delta t. Same thing can be done here. X prime is equal to x prime is equal to x plus delta x. Okay, so this is just another way of writing the definition of delta x. By adding it to x, you get x prime. But now this is equal to alpha x. Now I can do a trick here. I can take this expression and divide it by a number and then multiply by the same number, which shouldn't change anything, right? Dividing a number by another number and then multiplying it by that same number should not change it. So I take this x plus delta x and I'm going to divide it by x, whatever x is, and then I'm going to multiply it by x. Okay, so that is my alpha x. I'm just copying it from the previous line, but I immediately recognize now this as alpha. Right, there are x's on these sides, you're multiplying alpha by x, and alpha turns out to be this number here. So if you write alpha again explicitly, now in the numerator we have x plus delta x, you're dividing it by the denominator, which is x, which can be written by as x over x plus delta x over x, right? Just reviewing some really basic algebra, so please be patient. Okay, and x over x is just 1. So 1 plus delta x over x. Remember what I said about adding numbers or quantities that have the same dimension? Well, that applies to the quantity which doesn't have any dimension as well, which is 1. 1 is dimensionless. If 1 is dimensionless, so is delta x over x also dimensionless. Alpha here, we already know it's dimensionless, right? So everything is also dimensionless. It's very common to write this expression here. It's very common, you'll see it all the time, okay? Delta x over x, or delta t over t, if you apply the same logic to this variable t. You'll see it a lot. It's a ratio, a fraction, right? And you know, ratios are equal. I mean, you can write a ratio 1/2, but you also know that that's equal to 5 over 10. You can infinitely many ratios like this. So why don't we fix this? Meaning, why don't we take 100 and put it in the denominator here. All right, a number in the denominator, and then the numerator won't be delta t anymore. Let's just call it a number n. All right, so now I can write this as t prime is equal to, I'm using the same logic here, so alpha is 1 plus delta x over x, meaning t prime then is equal to 1 plus delta t over t times t, right? But now delta t over t is nothing but so n over 100. Times t. So this n here is called percent change. Percent change. All right. In our case, you go from 20 minutes to what? 40 minutes. How much is the change? What percent is the change? All right. It's not 2%. 2 is the factor. Remember, 2 is the factor that lets you go from 20 to 40. But when you talk about n, I called it n. You can call it m. Anything you like. We're talking about the percent change. So the change is 40 minus 20, 20, right? Delta t is 20 minutes, which is 40 minus 20. So this 20 divided by t, which was also 20, write it as a ratio here where you have the 100 as a denominator. And of course, the numerator is 100. So n is 100. Okay, 100% increase. All right, 100% increase is multiplication by 2. 50% increase would be and increase by 50. I'm sorry, 10, right? Half of 20 is 10, so 10 plus 20 gives you 30. T prime would be 30. All right, so what do you do then? You take the number, let's use x this time. The new x is x prime. You subtract the old x from it. This is delta x. And you divide it by the old x. And you multiply the whole thing by 100. Alright? That's what it means. This is equal to the percent change. Alright, so let's do it again here. Alpha x, x prime is equal to alpha x prime is equal to alpha, which is, okay, let me push here. So x prime is equal to alpha x, and alpha is 1 plus delta x over x, which we change to n over 100, this times x. Okay, so divide both sides by x. X prime over x is equal to, okay, not triangle, x prime over x is equal to 1 plus n over 100. And from here, subtract 1 from both sides. X prime over x minus 1 equals n over 100. Equate the denominators. X prime minus x divided by x equals n over 100. And then multiply both sides by 100 to get what we have here. Oops. This. Alright, so that's the formula for percent change. Alright, so let's go back to our table again. Let me write time, distance, let's add 2 more columns here, alpha, and then n, which represents percent change, right? So time is measured in minutes, 20, 40, 60, and then the distance traveled in those times were 1 mile, 2 miles, and 3 miles. And alpha, okay, in this row I don't have anything, but going from 20 to 40 or 1 to 2 requires a multiplication factor 2. Going from 1 to 3 or 20 to 60, alpha means 3, right? And 100% increase means either you go from 1 to 2 or 20 to 4. It doesn't matter, 100% increase. What about from 20 to 60? So you subtract 20 from 60, and then you divide it by 20, and then multiply by 100, right? So you have 40 over 20, that is 2 times 100, 200%. All right. Okay. Now remember what I said in the beginning? We had options. And now let's use option 1. Where was it? Here. Option 1. X can be any number and t can be any number. Alright? So when I say t from now on, I'm not talking about 20 minutes. T can be any of these 3 entries. Similarly, x can be any of these. Alright? So I'm going to write t here. And then x. Now, is there a relationship between x and t? Well, obviously there is, because whatever happens to time happens to distance as well. That's no coincidence, right? So can I write an equation that relates x to t? Okay, because I know that if I change t, x changes as well. They are proportional. Okay, if I triple the time spent, I'm tripling the distance. Okay, so there's a proportionality between the two, which is shown by this symbol here. This means proportional. Proportional to. It looks like an infinity symbol without this part here, right? It kind of looks like alpha too, but alpha is shorter like this. This one's a little bit longer. So it means proportional. And proportional means this: if I wished to write it as an equal instead of proportional. Now this is wrong because the left hand side does not agree the right hand side, either in numbers. I mean 20 is not equal to 1. Also in terms of dimensions. On the left hand side we have distance, which is represented by L. On the right hand side we have time, which is in t, capital T dimension. Okay, we need a factor here. Just like we can scale our time and distance separately, to go from one to another, we can also use factors. Okay, we don't call it scaling anymore because dimension changes, but it's still a factor in a way. Or you can call it a multiplication factor. Okay, sometimes you can call it a constant for certain cases, but let's not go there right now. A number here, okay? Well, this number, we can calculate the number, okay? What is the number that gives you 1 when multiplied by 20? Okay, it's 1 over 20, or 0.05. Okay, so if my x represents any number here, and my here, and t represents any number there, then I could just write 0.05 here, and I have a formula. Because I know that if I change my t from 40 to 60, my x will change accordingly, okay? Actually, it's always a good practice to use the units here. Include units, 0.05. Now, I need to be careful. X will be in what was it, not meters, it was in miles. Okay, so in order to have miles on the left hand side, I need to put miles here, but I'm going to multiply this whole thing by minutes. So I need something in the denominator which would take care of that. Okay, so let's write it in this form here. 0.05 miles per minute times t gives me my x. Okay, so having this formula, I could find any x for a given t. All right. Okay. That's also a factor, though. Let's give it a name. I mean, for this data, it's 0.05, but in general, I know that as long as I keep my pace the same, I will get a relationship like this, which is actually linear. We already defined what linear meant, right? T and x values, a straight line. So letters, I mean alphabetical, A, B, C, whatever you want to use. We can use A. Conventionally, the letter V is used. Let's use V. V, because the word velocity starts with V, right? So x equals Vt is what we have. a relationship between the two. So now that we switched from option 2 to option 1, x can represent any value. If I want to talk about specific data points, I'm not going to use the prime. Let's use the indices now. x1, x2, right? x1, x2, and x3, let's say. And then I have the corresponding time, t1, t2, and t3. But the relationship between those t values and the x values are always be similar. So v times t1, v times t2, v times t3 give you x1, x2, and x3 respectively. Okay? Now that works just fine for us. Now I can think of the ratios. Now what can I write here? I can write x1 over x2 is equal to vt1 over vt2. V's cancel, and I have t1 over t2. Just like I can write x1 over t1 equals x2 over t2. Actually, these are all equal to v, which is also equal to x3 over t3. Okay, I can do even more. How about this one? I could subtract x1 from x2 and take the ratio of that to t2 minus t1. And this will be equal to, do the same thing for the 2 and 3 pairs now, x3 minus x2 divided by t3 minus t2. And for this graph, what do they correspond to? Let's mark them. So we have roughly here t1, t2, and t3. Here x1, x2, and x3, right? Here. So if I do consider this one here, x2, okay. I'm subtracting x2 from x1. This is x2, x1. If I subtract it, what I end up is this length here, okay, or here, this one. That is x2 minus x1. Similarly, if I subtract t1 from t2, I get this, or that. t2 minus t1. Okay, that is called the slope of the line, and it's the same everywhere. This is what our v is. But it corresponds to the slope in our graphical representation. Okay, so this is the place where we see that a physical quantity corresponds to the physical property of a line, which is the slope of the line. The steeper this gets, means faster you're walking, or vice versa. If it's closer to the horizontal, this means you're walking really slow. Okay. Now, if you think about it, look at this equation here. Does this look similar to that? You may say, no, we have subtraction here. There's no subtraction there. But actually, they are the same. Because you can write this as x1 minus 0 divided by t1 minus 0. Okay, so instead of using points 1 and 2, I'm using now points 0 and 1. 0 meaning the point where the two axes start, they meet, which we call the origin. For this particular data set, the origin is right there. So x1 minus 0 over t1 minus t0 is the same as x2 minus 0, why not, right? t2 minus 0, that's equal to v. So it's pretty general, right? The slope, which corresponds to your speed in this case, doesn't change along the straight line, by the very definition of a straight line. So that's how you find it. But the important thing here, which we now have, is this: x equals vt. Okay, this looks like a formula, right? Formula for getting the distance in terms of time spent walking, if you're assuming a steady speed, walking speed. This works fine for our data here, which is this. Okay, what did I do here? I use a stopwatch to track my walking, and I measured the distance from my starting point, which is normal, right? Let's do something different now. This is the track that I'm walking. I'm walking this way to the right. All right. And the numbers here along this line are my x values: x1, x2, x3, x4, etc. Okay, and I'm just going to put the general x here representing distance. Okay, x1 doesn't have to be 0. It can be any number. If it is not 0, what does it mean? Maybe it means those numbers are still measuring the distance, but from, let's say, my house here. So I leave my house driving, okay? I drive for a mile, 1 mile, and then I walk for 1 mile. I walk for another 1 mile, okay? But the numbers here, x1 is 1, x2 is 2. x1, 1, x3 is 3. These represent something else, right? So let's make our table again. T values. I'm still using the same time, I'm just starting my stopwatch right here at the beginning of the trail. So T values will not change. 20, 40, 60. But my X values, 1, 2, and 3, mean different things. Okay? These X is not the distance, but its position. Okay? X is the position variable, not distance, not displacement. Okay? When I mean delta X, I'm talking about displacement. It is distance, in a way, from your origin, but the position is actually the coordinate. That's what we call it, the coordinate. It describes a location rather than a distance traveled. Because why? I mean, 1 mile, if I just say 1 mile, I don't know if I'm measuring a distance from my house to the park Or am I measuring the 2 points from, let's say, from x2 to x3? I don't know, right? Both work for displacement. But if I say x3 is equal to 3, I'm referring to a point rather than a distance. Okay? That's a different usage of the variable x. And the equation I have that corresponds to this relationship is a little different. Okay, so let's add a constant. Okay, now Vt plus a constant. Now how about we do this? Let's C represent this 1 mile that is extra, okay? And then every time a 20-minute passes, I travel an extra mile, and those will be coming from the first term here. All right. So let's correct one thing though. Now the t values will not start from 20. It's going to start from 0 actually, because I said you start your stopwatch when you are at the beginning of the trail, right? So let's replace this 20, 40, and 60, and let's make these 0 and 1 and 2. Okay, so t still tells you the time spent while walking, but now x refers to the location, where you are, how far you are away from your house, right? So t, I'm sorry, I didn't mean 1 and 2, sorry. I meant 20, 20, and 40. Because that's what we had in the beginning, right? For 40, we said in 20 minutes you walk for a mile, and in 60 minutes you walk for 3 miles. So if you walk for 2 miles plus 1 mile, you have 3 miles distance from your house. But that's when 40 minutes has passed. After an hour, you're 3 miles away from your starting point, but you're 4 miles away from your home, okay? So if you do it, okay, you don't really change much. You can still write x equals 0.05 miles per minute times t, but now you add a mile here, plus 1 mile. Okay, and I haven't violated any rules about adding and subtracting regarding dimensions, I mean, right? Because the dimension of 1 mile is L, dimension of x is L, and the dimension of 0.05 times t is also L. Okay, I have my table. What about my graph then? So if I go back to this method of plotting, t, time, and then distance. Well, this time, x represents actually your location, your position. Okay, so when t is 0, I'm already at 1. Let this be 1. This is 2, 3, and 4, right? So when I start my stopwatch, I'm already 1 mile away from my home, so the first point is here. The second point, when t is 20, that's when I'm 2 miles away from home, so the point is right there. Similarly, 40 corresponds to 3. And after an hour, these are in minutes, these are in miles. After another 20 minutes, I'll be at 4 miles from home. Okay, this looks different from my first graph, but not too different. The first graph, well, it looked like this. Where is the actual graph that I drew? Let me zoom out. Okay, my roller doesn't work here. Okay, zooming out. Here, up here. Oops. This was the graph, okay? So this looks different from that. It doesn't go through 0. The intercept is not 0. Okay, I'm going to go back to the original zoom level. This mouse is not cooperating, I'm sorry. Okay, let's go back to the 100% zoom. Oops. I guess I should go mess with the zoom, huh? Let me try one more time. Okay. Okay, good enough. So I can still connect these dots, or let's say go through those dots with a linear fit, but the intercept is 1, which you already knew, right? Because if you think about the equation of a straight line from your analytical geometry class, maybe they showed you this equation, y equals mx plus b. I'm just using different letters. Instead of M, I'm using V. Instead of B, I have C. That's pretty much the same equation. The other one, when we had this before, x equals just Vt, where x meant the distance you traveled, our graph was like this. But now it's shifted, okay? Its slope did not change, it just shifted above. This means you can have as many as you want, okay? You can add more lines here, as long as they're parallel to the original line. They all represent the same thing. You're just walking in the park, but you're just changing your origin, your reference point, okay? Are you measuring the distances from your house or from HEB, all right? So that's what matters. As long as you're keeping the slope the same, this means you're talking about the same thing, walking with the same pace. Okay, what about those percent changes and all that, all right? How does it work now? Now remember what I said earlier about t and x? Like I used the primes, right? And I said t prime was equal to alpha t, and then x prime was equal to beta x, but alpha was equal to beta. Now it won't be like that anymore, all right? It won't be like that. Now let's do the same notation again. So x prime beta x, right? So x prime here, which corresponds to x plus delta x, is now equal to beta x, where beta is equal to 1 plus n over 100 times x, that's x prime. But if I want to do the same thing for t prime, t plus delta t is equal to alpha. Now I may have used alpha and beta the other way around, doesn't matter. Alpha t is equal to, now if this alpha is not equal to beta, then I can't use n anymore, it'll be m over 100 times t. It's still a linear relationship, okay, this formula x equals vt plus c is still linear. By the way, what would be nonlinear? Nonlinear would be a power here, anything but 1. So v times t to the power 1 is linear. If you have 2, 3, 4, it'll be nonlinear, or 1/2 or 0.7. Anything but 1 would be nonlinear. In nature, you have many nonlinear. You have more nonlinear processes than linear. Linear is actually a first order approximation, right? But in our case, for this equation here that we have now, as opposed to this one, things are a little bit different as we see now, okay? First of all, x doesn't correspond to a distance, it corresponds to a position. And then, when I think in terms of scaling my variables separately, I have to use separate factors, and I will not have the equations with ratios that I had before. So let's give it a test, okay? We have our data here. Let's add alpha and beta. And let's add n and m, just for exercise. Right? So alpha was the factor. Now I can't do anything. Is alpha 4 t? Alpha is 4 t. Well, anything multiplied by 0 is 0. So let's start. Okay, what should we do here? Doesn't really apply, huh? Okay, let's just start from here, from 20 again. So going from 20 to 40, so I'm going to put a negative here. Going from 20 to 40, alpha is 2. All right, let me erase this here. This one. Okay, and then going from, let's say, 20 to 40, alpha will be 3. But going from 2 to 3, beta would be 3/2. And going from 2 to 4, you have a factor of 2. Now, n represents the percent increase in x. All right, so 2 to 3 is 50%, 2 to 4, 100%, 20 to 40, it is 100%. Okay, so not the same. And going from 20 to 40, it's 200%. Right? You subtract 20 from 60, that is 40. 40 divided by original value 20, that is 2 times 100, 200. So although those factors are not the same, for the linear relationship we have right now with Vt plus c, we still see some rule here, right? Like going to whatever happens to alpha, let's say. Okay, I think I made a mistake with m here. M was the percent change in time. So 200, okay, it's correct, and right, fine. But n was the percent change in x, and that's also correct. Okay, no, fine, no problem. Okay, so the ratios, yeah, I was talking about ratios. Ratios don't work. So 60 divided by 20 is not equal to 4 divided by 2, right? So, where else do we see these? I think the book has some geometrical volume and area calculations. Let's start with area. You have a disk, let's say, of diameter equal to 4, which means radius is 2 inches. What will be the area then? Area is found by this formula, pi r squared, right? So just plug in the number here for r and multiply by pi, and you get the area. Now what if you scale the radius, and r prime is now 2r? So now d is, let's say, what, 8 inches. And if you calculate the area, call it a prime, it will not be equal to 2a, all right? It will not be. Why? Well, very simple. A prime is equal to pi times r prime squared. But r prime is equal to, remember we doubled the size or the distance, is equal to 2r. This square applies to both 2 and r, so 4 times r squared, or 4 pi r squared equals 4a. So by changing the radius by a factor of 2, you're increasing the area by a factor of 4. Okay, you're quadrupling. If you go to volumes, then the formula has an r cubed in it, like the volume of a sphere, let's say, a 3D object with some radius. Then the volume is 4/3 pi r cubed. Let's say v is 1. What will be v prime? Okay. Now I don't have to tell you what r is. R can be found using this formula, of course, but let's say you don't know what r is. You just know that r prime is equal to 2r. You have a change in the volume. So what is v prime now? Okay. So to solve problems like this, you have to write proportions using the formula. So think about v prime over v. What is it equal to? V prime, according to this formula, is equal to 4/3 pi r prime cubed, and v is equal to 4/3 pi r cubed. 4/3 cancel, pi's cancel, and you have r prime cubed over r cubed, or r prime over r to the power 3. And r prime over r is 2. 2 to the power 3 is 8. Alright, so you have an increase in the volume of the sphere. It's 8 times bigger. It contains 8 times larger volume if you just double the radius. Okay, and what is the percent change? Then you have to subtract 1 from 8 to get 7 divided by 1 was the original volume, right? Times 100, what, 700% change, right? So this is so widely used, so you better get used to this kind of reasoning, okay? So you don't need to calculate r first and then take that r, plug it in here, calculate r prime, and then calculate v prime. You can just write a ratio like this, get rid of the things that they cancel, and then you have your answer. Alright, so to summarize, okay, from now on we're going to use variables, and we're going to use linear relationships a lot. So if I write x equals vt plus a constant, let's use the letter x naught this time, or x0 instead of c. I mean, they all mean the same thing. But if I write this, it's very common. I'm talking about the change of coordinates, x, okay, location with time, and x naught will be defined as the position when t is 0. Intercept, or your graph, right? Something like that. The intercept here is x naught. Okay, so again, scaling means multiplying a quantity by a dimensionless number. You can go from 1 meter to 2 meters. You're just scaling. You can go from 1 hour to 24 hours. Dimension doesn't change, still same number. But there are also proportionalities. You go from one physical quantity to another physical quantity in this form, in this equation here. Okay? Given time, what is x? Then you have to multiply with a variable that does have a dimension. In this case, its dimension is L over T. I'm talking about V here. Its dimension is L over T, right? And in the most general case, it's not just V times T, but you add something here, this intercept. That's the most general case, although there are special cases where x naught can be 0, right? C can be 0. Special case, but in general, it's a non-zero number. And V can be 0 sometimes, right? Can be positive, can be negative. X naught can be positive, 0, or negative. You have all these possibilities. Actually, if you think about physical variables, the only thing that cannot be negative is t. There is no negative time. Time is always positive. But in general, physical quantities can have negative or positive values. All right? Okay, I'm going to stop here and then maybe talk about other things in the first chapter, like maybe unit systems, how to go from one unit system to another unit system, and more on dimensional analysis. And there's also the topic of scientific notation and significant figures. Okay, But let me stop this recording right here.